Welcome, boys and girls, to Earth Science Rocks. Now today's video is Extreme Topo, and here's Jason.
Thanks, Walt. I'm here with my friend Simon on Huckleberry Island in Lake George. We want to teach you what a topographic map is and how to use one.
Topographic maps are maps that show elevation using contour lines. So we can sometimes call these maps contour maps.
An isoline is a line that connects points of equal value. On a topographic map, the lines connect points of equal elevation, so we call them contour lines.
In this shoreline on Lake George, the water line acts as a natural contour line. Any point on the water line has an equal elevation. The top of the white line, the high water line, acts as a second contour line. Imagine these lines as we move out on the lake.
Contour lines are often parallel and always form loops or run off the map. They never stop on the map. And if they're going to form a loop, it's often around a mountain.
The contour interval is the change in elevation between contour lines. The contour interval remains constant between any two lines on the map.
Okay, so I get these iso lines, but what are the contour intervals about?
Over there is Shelving Rock Mountain. Let's say I wanted to know how tall it is. I could just hike it with a GPS and find out.
Ah, the batteries are dead.
Or I could just find the contour interval and count the lines. On this map, the contour interval between the thick lines is 100 feet. And there are 1, 2, 3, 4, 5, 6, 7, 8 lines between the lake and the top of the mountain. So the mountain rises 800 feet above Lake George. But wait, there's more!
Now you know that Shelving Rock Mountain is 800 feet above Lake George. Question is, what is its elevation above sea level?
Now it says here on the map that Lake George is 320 feet above sea level.
Thanks, Walt. So, if we add 800 feet to 320 feet, we now know that Shelving Rock Mountain is 1,120 feet tall. But if you want to be a little more accurate, you could use the contour lines on the map. If you look at the small contour interval, you would see it's 20 feet. So the summit of Shelving Rock Mountain is 1.5 of these small lines above 1,100 feet. So the actual elevation of Shelving Rock Mountain is 1,130 feet above sea level.
Oh, I get it. Woo! That mountain over there is 800 feet tall. We need to find out how steep it is to get up the side of it.
Slope and gradient are two other words for steepness. There's two ways to find out how steep a slope is. One way is to look at how close the contour lines are on a map. The closer the lines are together, the steeper the slope.
Here's a spot where the lines are really close together on Sleeping Beauty Mountain. Let's check it out.
Okay.
Here we are in Sleeping Beauty Mountain in the Adirondacks. As you can see, the slope is really steep. If the contour interval was 20 feet and there is a line right at my feet, there'd be another contour line 20 feet straight above my head and a contour line 20 feet straight below my feet. If you're looking down from above, like on a contour map, it would look like these lines were touching each other. The steeper the slope, the closer together the lines. Let's go find someplace that's not quite so steep, like maybe Warren County Airport.
So here the land is really flat. If the contour lines were 20 feet apart, the other line, if I was standing on one, the other contour line would be way on the other side of the airport. If you were up above, like looking at a contour map, the lines would be very far apart.
But here the slope is just right. It's not too flat, it's not too steep, it's just right.
There is a more accurate way to find gradient. The formula is in your earth science reference tables. Gradient equals change in field value over change in distance. So to answer the hiker's question about how steep Shelving Rock Mountain is, you would have to find out how tall it is and divide that by the distance from the base to the top.
Well, we already know that the mountain is 800 feet tall from the bottom to the top.
I'll go figure out how far it is.
No, Jason, we can use the map. Using the contour map, you can figure out your distance from your start point, which is where we are here, to the summit. So I draw a line at the start point to the summit, and then there's a scale, which is in miles. I make sure my start point is lined up with the 0, and if I travel along the scale, I can see that 0.5 miles would be the total distance that we're going to travel.
So, gradient equals change in field value divided by distance. In this case, the gradient equals 800 feet divided by 0.5 miles, making the gradient 1,600 feet per mile.
And don't forget, always remember your units.
Let's do it!
Nice profile.
Why, thank you.
Not you, the mountains.
Not only are profiles beautiful, they're useful. If you can make a profile on a map and compare it to a profile in real life, you can name peaks on the horizon or even find out where you are. A profile is made on a contour map by drawing a straight line between 2 points that would represent the horizon. You then measure the elevation of every contour line where it crosses the profile line. You'll transfer that information to a graph. On your graph, the profile line will make your x-axis, while elevation will be your y-axis. The resulting plot will be your profile. Have your teacher show you. Let's compare this profile photograph of Buck Mountain and Pilot Knob to the profile line on the map above. In the photograph, you can see 2 peaks with a valley in between, and the left peak is taller. Can you see this on the map? Which side of Pilot Knob Mountain is steeper? And how is this shown on the map? Hopefully, you can see profiles are one of the best ways to bring contour maps to life.
Whoopsie daisy, whoopsie daisy! Guys, you forgot stream flow!
Hey, I got a great idea. Let's talk about stream flow.
That's a great idea. Streams all flow south.
No,
Ow.
they flow north.
Actually, they go downhill!
Oh yeah! There are 3 ways to determine the direction a stream flows in.
If the ocean is on the map, then the streams are going to flow into the ocean. But this isn't true for lakes and ponds. Streams will flow both into and out of lakes and ponds.
If there is no ocean, you can look at the values of the contour lines along the stream. All streams flow from high values to low values, or downhill.
If you can't find the values of the lines, then you're going to have to use the V's on the map. Let me show you. Here we are in a small valley in New York State. Here we are in the same valley with contour lines. The ribbon connects points of equal elevation. The stream flows out of the V's, or you could say that the V's point uphill.
Once you figure out what way the stream flows, use the compass on the map to determine the direction the stream flows from. For example, from northwest to southeast.
All this talk about contour maps has put me in a depression.
Did somebody say depression? A depression is a low point on a contour map that's uphill on all sides, like this rock quarry in Glens Falls. A depression is different from a valley because a valley has an outlet. A depression is shown on a contour map using hatcher lines. Because depressions have no outlet, water collects in the bottom of them. If humans want to keep depressions dry, they must pump the water out with pumps like that one.
Let's review what we've learned. A topographic map is a map that shows elevation using contour lines.
A contour line is a line that connects points of equal elevation.
The contour interval is a change in elevation between contour lines on a map.
Gradient is how steep the land is. The closer the lines on a contour map, the steeper the gradient.
Gradient equals change in field value over distance.
A profile is a side view of a contour map and is useful for visualizing landforms.
A profile is constructed by graphing the elevation of the contour lines that cross a profile line.
Streams flow out of the V's towards oceans and downhill.
A depression is a low area with no outlet.
Depressions are often shown using hatcher lines. Well, we hope you learned a lot about topographic maps today.
Until the next Earth Science Rocks, have a nice day!
I slipped away further from you, trying to find what